Good morning, students. Today we will start a new chapter, Chapter 5, Electromagnetic Induction and Alternating Currents. Can you think of a situation now where we live without electricity? It will be very difficult, right? If we don't have electricity at home, even this meeting is not possible. And we won't be using any of the gadgets, and we won't be having even light, fan, AC, none of the electrical appliances. So it will be very hard to live without electricity. So, what made it possible to generate electric current at a large scale and send it to people at different places? It's one phenomenon called electromagnetic induction. So, in this chapter, we will learn the basics of electromagnetic induction, how it was discovered, and how using that generators are made, and how using transformers their values are changed and they are uh, given to different places, distributed among houses everywhere. And also we will learn something about alternating currents, some properties of alternating currents. All the supply current which we receive are alternating current. So let us start this chapter. This is a smaller chapter compared to our previous one, and it is simpler. There are not much mathematical derivations. So I hope you will like this chapter. So we are starting off with the new chapter, Chapter 5, Electromagnetic Induction and Alternating Current. So we will see how a generator works. This is a simple of that. And also we will see the working of transformers, which are necessary for the distribution of electric current produced at one place. And then we will also see some properties of the alternating current which we are using on a daily basis. So, what is meant by electromagnetic induction? Have you learned about electromagnetic induction before in any of your lower classes? Have you learned about electromagnetic induction?
Yes, teacher,
Yeah.
to heat any solid substances with the help of magnet, right? This one,
Huh?
this induction.
Yeah, that's not the thing. Oh, maybe you are thinking of the induction cooker.
Maybe.
Yeah, there is this idea, but it's not basically heating a substance. Let us see what is meant by electromagnetic induction. The phenomena in which electric current is generated by varying magnetic fields is called electromagnetic induction. The last chapter we learned how a magnetic field is produced by electric current. This is just the reverse, that electric current is produced by magnetic fields. But there is one condition, the magnetic fields must be varying. So this varying is very important. If the magnetic fields are not varying, they cannot generate electric current. So what is meant by electromagnetic induction? It's a phenomenon in which the electric current is generated by varying magnetic fields. So we will see that in detail. Now, electromagnetic induction is very cost effective. We have a lot of power generating ideas, like there are hydroelectric power generator, thermal power generators, steam generators, generators where we use nuclear power. All these generators, the basic idea which is employed is electromagnetic induction, because it is very cost effective. The amount of energy utilized there in producing electric current is not much compared to the result. So it's very cost effective. That is why this idea is used around the globe to produce electric current and distribute it around. And electromagnetic induction, as the name suggests, is related with electricity. Electro means electricity, magnetism, magnetic, and also induction. We have already learned in our previous chapters current, electricity and magnetism, details about electricity and magnetism. But this word induction may be relatively new to you. What is the meaning of the word induction? The word induction means to induce something or to generate something or to produce something. So here we will see many occasions where current is produced, EMF is produced. So we won't use the word produce. Instead, we will use the word induced. So induced means produced, generated, or created. So here in this chapter, whenever you feel like it is generated, produced, use the word induced. That will make it more technical. So for induction, it means to induce something or to generate something. Now, therefore, electromagnetic induction means induction of electric current due to magnetic field. That is, production of electric current by magnetic field. It should be varying magnetic field, don't forget that. We'll see that in detail. Now, how did we get to know about electromagnetic induction? Who first discovered electromagnetic induction? In fact, three scientists, Michael Faraday from UK, Henry from US, and Lenz from Russia. These three scientists, in a similar period of time, did a series of experiments, and they found out or they discovered this phenomenon called electromagnetic induction. But the first person to publish the results was Michael Faraday. So now the world knows electromagnetic induction as proposed and developed by Michael Faraday, because he's the one who first published the results. Even though all three of those scientists did the experiments and came up with almost similar results at a similar period of time. So, who developed electromagnetic induction?
Michael Faraday.
Michael Faraday. It's
Faraday.
yeah, it's Michael Faraday. But we don't forget the names of Henry and Lenz, because Henry is the unit
Teacher,
for, yes,
did Michael Faraday discovered Fahrenheit?
no,
No. Acha,
no.
okay.
Michael Faraday's name, I have never heard it.
No, teacher. He has one. His in his name we give unit F, right? In something.
Farad for
Farad. Yes. Yes.
capacitance.
Ah.
Capacitance
Yeah. 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 Yeah.
in Farad. That is
Yes.
in honor of his name. Yeah, that's true.
Yes.
Because it's all related, electricity, magnetism. So it's all related. So in honor of Michael Faraday, we name the unit of capacitance as Farad. It's not Fahrenheit, okay? That's totally different. So Henry, the name Henry is kept as a unit of inductance, which we will learn later in this chapter. And also there are three laws of electromagnetic induction. First two laws are by Faraday and the third law is by Lenz. So even though the credit goes to Michael Faraday, the names of Henry and Lenz are still remembered for their contribution in the field. So it's their electromagnetic induction that led to the development of modern day generators and transformers. You know, generators and transformers are essential for the large scale production of electric current and its distribution. So we will see the experiments performed by Michael Faraday. We will also study how magnetic field can produce current in the conductor. So what we are doing in this lesson is we will see three experiments conducted by Michael Faraday. Is that clear to you? What is electromagnetic induction? It's just
Yes.
an
Yes.
introduction.
Yes, teacher.
So let us see the experiments conducted by Michael Faraday. So this is Michael Faraday. I'm sure you must have seen this picture before. So, one of the scientists, Michael Faraday, performed a series of experiments, and based on the results, he gave the law of induction. And he introduced the phenomenon of electromagnetic induction. It's in his name because he was the first one to publish the results. Now, let us see his first experiment. In the first experiment, Michael Faraday took a coil and attached a galvanometer to it. Here you can see a coil of a wire which is wound like a helix or a spring, and it is connected to a galvanometer. What do we use a galvanometer for?
Measuring current, the flow of current.
No, no,
To,
yeah,
No,
to
no.
understand there is a flow of current or not.
to
Yes.
know whether there is current flow in the circuit or no. So the galvanometer will show in the zero deflection. Then we say that there is no current, and if it deflects to one side, there will be current in one direction, and if it deflects to the other side, there will be current in the opposite direction. So galvanometer is used in a circuit to identify whether there is current flowing through the circuit. So this is one of the things which he took, a coil of wire attached to a galvanometer. Is there a battery or a source of current here? Nothing. There
No,
is
no.
no battery, which means there cannot be any current. And he brought a magnet near the coil. Here you can see a magnet, and these are magnetic field lines that represents the presence of a magnetic field. We know that around a bar magnet there will be magnetic field lines, or there will be magnetic field. So these lines represent the presence of a magnetic field around this bar magnet. He brought the magnet near the coil. When the magnet is moved towards the coil, the galvanometer showed deflection. What does that mean?
Means
There is a presence of current.
There is presence of current. But is there a battery or a cell? No. So just when you move the bar magnet, what happened? Without a battery, without a cell, current is generated. Or now we will call it as current is induced in the coil of wire. That is why the galvanometer showed deflection. So just by moving a bar magnet into the coil, what happened? The current is induced inside the coil. That was shown by the deflection of a galvanometer. Galvanometer even showed the deflection in the opposite direction when the magnet is taken away from the coil. So when you put the bar magnet into the coil from one direction, it showed deflection in one direction. Now when you remove the bar magnet from the coil, it shows deflection in the opposite direction, which means the current is now flowing in the opposite direction. So the galvanometer, if you are moving into, if it is deflecting to one side, and if you take it away, it deflects to the opposite side. So when you keep on moving, what will happen? When you keep on moving the bar magnet into the coil and out of the coil, what can you see for the galvanometer? You will see that the galvanometer deflects in the opposite direction continuously, which means there is a current produced which changes its direction continuously when you are moving the bar magnet into the coil and out of the coil. So when the magnet was not move, there was no deflection in the galvanometer. If the bar magnet was kept outside the coil stationary, then there was no deflection. If you keep the bar magnet inside the coil, when you move, there is deflection. But if you keep it there inside the coil, as you can see here, and you don't move it, you just keep it there, then also there is no deflection. So only when the bar magnet is either moving into the coil or out of the coil, there is deflection. So faster the magnet is moved, the more is the deflection in the galvanometer.
Teacher, what is deflection?
Deflection means, say, suppose this is the pointer in a galvanometer, my finger, okay? This is deflection, okay?
Oh,
This is deflection. Deflection means moving from its original position.
teacher, it means if the magnet moves only, there will be current, right?
Yeah, then only there is current. Now, if it is stationary, either uh, outside the coil or inside the coil, if it is not moving, there is no deflection, which means there is no current. Only if there is deflection in the galvanometer, at that time there will be current in the coil. Is that
Teacher,
clear? Yes.
what if we move the cell only, not the magnet?
Not the magnet, only the coil. That was a second experiment. Then also there
Acha.
was deflection. We will see that as a second experiment. Okay, so that's a good question. So he also thought like that. What if you don't move the bar magnet, move only the coil? But the result was same. And he found that faster the magnet is moved, the more is the deflection in the galvanometer. This showed more and more current flows if the magnet is moved very fast. So if you are moving it faster, more deflection. It will bend a lot, which means more current. Now, if you are moving it slowly, the deflection will also be small, which means a less amount of current is produced. So faster the magnet moves, more deflection in the galvanometer. And so more current is produced in the coil. Now the same effect was observed is that if the coil is moved and the magnet was not moved. You ask this doubt, right? So even if the bar magnet is kept constant and instead of the bar magnet, you move the coil, keep it into the bar magnet, out of the bar magnet. Then also the result is same. That is whenever there is motion, then a current is produced.
Teacher,
Yes.
how the current is produced when there is the magnet is in motion?
When the magnet is in motion, then
Yeah.
we have learned in the previous chapter, remember that a magnetic field will produce force on the charge carriers. We have learned that, right?
Ah, yes.
So this metal wire will have charge carriers, but there is no cell or battery that will push it to move. So
Hmm.
some kind of force should be acting on the charge particle that will make it move.
Yes, teacher,
So,
understood.
mentally, you can just imagine like the charge carriers are simply staying inside the metal wire. Now there comes a magnetic field, they experience some force, and this magnetic field is keeping on changing, so the charges can no more sit idle inside the conductor and they starts moving. That is called current. So this can be a Mendel picture. So and it can be seen that there is current flowing, so it will be true. So some effect was observed if the same effect was observed if the coil is moved and the magnet was not moved. Now, from this experiment, the final observation or the conclusion made by Faraday is that relative motion between magnet and coil induced electric current in the coil. Why he told relative motion? Suppose you keep the magnet inside the coil and move both the coil and the magnet in the same direction with the same speed. Is there a relative motion between them?
No.
No. So if they both of them are moving in the same direction with the same velocity, there is no current. Only if one is moving, other stationary with respect to it, then only there will be current produced. So relative motion is important, not just motion. It should be relative motion. One of them should be stationary and the other should be moving. So relative motion between the magnet and the coil induce electric current in the coil. And faster the movement, more current is reduced. And the movement can be either for the coil or for the bar magnet. So is this experiment clear to you?
Yes,
Yes,
teacher.
teacher.
So let us see the next experiment, which is a similar one, but with small difference. Okay. So let us see the next experiment. Faraday's experiment number 2. Now, Faraday took a coil connected to a galvanometer. As you can see here, there is a single coil which is connected to a galvanometer. But instead of taking a magnet, he took another coil which was connected to the battery. Here you can see another coil of wire wound in the form of a helix or a spring, and it is connected to a battery. Oh, what I have written here is wrong. It should be connected to a battery. That's by mistake I wrote with a magnet. So here he took another coil of wire connected to a battery. So this coil, which is attached to a battery, will have current in that. When the coil attached with battery was brought near another coil, the galvanometer showed deflection. So when you just move this coil with the battery into the near to the other coil, what happens? It shows deflection. Galvanometer shows deflection. What does that mean?
Presence of current.
Presence of current. So let me call this coil, one single coil, as the first coil, and this as the second coil, which we are bringing near to it. Similarly, when you take it away, then what happens? Then also there is deflection, because the same phenomenon repeated as we saw in the first experiment, even when there was no magnet. Can you guess why? Even when there was no magnet, the same effect as if this is a bar magnet was there. Can you guess why?
It's electromagnet, right?
It's like an electromagnet. So when current flows through a coil of wire, it will produce magnetic field lines in between. A current carrying wire will produce magnetic field. So more number of turns, you know that stronger magnetic field is produced. You did a problem for a straight wire, less magnetic field. For a single wire, in the middle, you will get a little higher magnetic field. Now, if it is made into very small, many turns, like in the problem in the test, you saw that the magnetic field becomes 100 times if the same wire was wound into 10 turns, right? So if this wire is wound into small circles with large number of turns, a strong magnetic field is produced, or this acts similar to a bar magnet. That is why the same phenomena as we saw in the previous experiment repeated even when there was no magnet. This can act as a magnet. This shows that current flowing in one coil was able to induce current in another coil when there is relative motion between them. Again, I would like to say that when you move this coil into the first coil, when you move the second coil into the first coil, and if they are remaining stationary with respect to each other, there is no deflection in the galvanometer. Only when you move in, there is deflection, and when you move it out, there will be deflection in the opposite direction. Just as you asked previously, if you are keeping this a coil attached to the battery stationary and move the first coil, then also the result is same. So the final observation is that when there is relative motion between coils, it induces electric current. Is this clear to you?
Teacher,
Yes,
Yes.
teacher.
I didn't understand the last point, the relative motion one.
If there is relative motion between coils, it induces the electric current because one of the coils are connected to a battery. So this will act as a bar magnet. So it is just the same as what we observed in the previous experiment. The difference is only that instead of a bar magnet, we took a coil of wire attached to a battery. So this will act as a bar magnet. Relative motion means if the coil of wire and the both the coils of wires, if they are moving together with the same velocity in the same direction, there is no deflection of galvanometer, which means in the first coil, current is not induced. But if one is kept stationary and the other is moved, then it will induce current in the first coil. So only if there is relative motion, there is induction of electric current. Is it clear?
Yes.
Yes.
Yeah, because if both of them are moving together with same velocity, there will be no deflection of the galvanometer because there is no relative motion. Always one of them should remain stationary and the other should move, which we call relative motion.
Teacher,
Yes.
what if both are moving with different velocities? Then it may
Then
be,
also there is relative motion, there will be
yeah,
deflection.
then, okay.
Then also there will be relative motion with a velocity which is equal to the difference in their values, right? So there will be relative motion between the bodies. Is that clear now?
Yes, teacher.
Also, if they are moving with same magnitude velocity but in different direction, if we move them like this, then also there will be deflection in the galvanometer showing the presence of electric current. Okay, so whatever way there is relative motion, then there will be induction of electric current. So let us see Faraday's experiment number 3. From the first experiment and the second experiment, we have a tendency to think that it is motion that is inducing electric current. So Michael Faraday also wanted to verify whether it is the motion that is, whether it is the relative motion between the two coils, which is essential for the induction of current. So in this third experiment, he wanted to verify whether the relative motion between the two coils is essential for the induction of current. So what he did, now he didn't move both of the coils. Both coils are at rest. So he took in this case a coil connected to a galvanometer and one more coil attached with the battery. As you can see here, the first coil is connected to a galvanometer. The second coil is connected to a battery, but there is a switch also. This is a closed switch. Okay. When the circuit was open, there was no current flowing through the coil. So this is the key open. Switch is open. So when the switch is open, no current is flowing through the coil. So what will be the magnetic field produced by this coil when it is open? Zero.
0.
Zero. Zero Tesla. But as soon as the circuit was switched on, there was deflection in the galvanometer. So as soon as switch on, the battery will flow current through the coil. So what will happen? Will there be a magnetic field? Yes. Suppose it produced 5 Tesla. 5 Tesla is a large amount. It's an exaggeration. I know that. But still, let us see. When the key is opened, the magnetic field is 0 Tesla. Now, when they switch on, then the magnetic field suddenly increases to 5 Tesla. Then what happened? But as soon as the circuit was switched on, there was deflection in the galvanometer. See, both of them are not moving. But when I switched on, the magnetic field increases from 0 to 5 Tesla, and suddenly the galvanometer shows a deflection in the coil which is kept near to it. Now, when the circuit was on continuously for a long period, there was no current. When the circuit was continuously on for a long period means the magnetic field remains the same, 5 Tesla itself. Then there is no deflection of the galvanometer, which means no current is produced then. Okay. Now, when the circuit is switched off, then what happens? Suddenly there is a deflection in the opposite direction. Okay, when the circuit was switched off, which means the magnetic field now again came back from 5 Tesla to 0. There is a change in the magnetic field. Then what happened? A galvanometer showed deflection. So whenever the current is switched on and off, at that moment there is deflection. But if you keep it on, the magnetic field remains the same. There is no deflection. If you keep it off, there is no magnetic field. The situation is same, so there is no deflection. Is that clear? Is that
Yes,
clear?
teacher.
So, is movement necessary? Is relative motion essential?
Yeah, for both, for other two experiment, but for the third one, it's not necessary.
It's not necessary. So even without moving them, we can produce electric current. What we have to do? We have to do switch on and off. When we switch on and off, what is changing? The magnetic field linked with this coil is changing. So do you remember in the first slide or in the beginning of this lesson, I told varying magnetic field is necessary. So the magnetic field should vary either by moving or by switching on and off. So only varying magnetic field is necessary. Motion is not necessary. He observed that the galvanometer showed momentary deflection only when the system was undergoing a change. So variation in the magnetic field is absolutely necessary. So the final observation is that relative motion is not an absolute requirement for inducing current. There is induced current only when there is a change in the system. Okay, and the change can be either by motion or by increase and decrease of the magnetic field itself. So based on these three experiments, Faraday gave two laws of induction, which we will learn in the next class. So are these three experiments clear to you?
Clear, teacher.
So from this lesson, we learned
Teacher,
what is electromagnetic
teacher,
induction.
next
Yes.
class, can you please again the experiment 3? I didn't understand this.
Experiment 3, you didn't understand well.
Yeah, teacher.
Okay. Okay, we will just have a revision of experiment 3 in the next class.
Okay, teacher.
Okay, so the result is that even if there is no movement, if the magnetic field is increasing and decreasing, which means the magnetic field near the coil is varying, there will be a current induced in the coil. Here in this experiment, both of them are not moving, but we are opening and closing
Yes,
this.
teacher.
Is it clear, Irfan? Should I repeat next class?
No, teacher, it's clear.
Okay, okay. So I will upload this as a video and watch the video, this part, if you have still have a doubt. I hope this is pretty clear to you. This will be clear to you if you hear once again. Okay, so we will conclude the lesson here. And see you in the next class.